Good morning, everyone. Hope all is well. Hope everyone's doing all right. Sorry about that. Had an alarm on. All right, looks like everybody's in. Hope everybody's doing great. Hope everybody enjoyed their spring break. Ready to get the rest of the semester on the way. It's countdown time now. Every week that passes, the closer we're gonna get to the closing out the semester. So should be excited. See something in the chat. Good morning. Good morning. All right. And appreciate for those who tuned in on Monday, helping Pod Day be a success. Yep, only 8 weeks left. Only 8 weeks left. And so we closed out last time we talked with chapter 6. Yep. Yeah, this time will go by fast if you're not careful. So yeah, was that something? Okay. All right. So last class we talked. Last lecture we did. We closed out chapter 6. So today we're looking to get into chapter 7. All right, which is probabilities, not probabilities, properties of normal distribution. All right. So probability distribution functions, PDF for short, is an equation used to compute probabilities of continuous random variables. Oh, also I didn't mention, you see the graph, we talked about it before, normal distribution, that bell-shaped curve. So that's why I drew that right here. We're going to be leaning on that distribution. And also we only have 2 sections in chapter 7. So it's just 7.1 and 7.2. So either we'll do both today and leave tomorrow as a review. Oh, well, I'll probably do one today and one tomorrow, one next class. No, hold on. Today is Monday. I mean, today's Wednesday. We didn't do class Monday. Anyway, I'll think about it as we go through. Yes, sir. Yes, sir. So in order for it to fit, the probability distribution function must satisfy the following 2 properties. So the total area under the graph must equal to 1. Then the height of the graph must be greater than or equal to 0 for all possible values. So the area under the curve, we'll scroll up, talking about this purple shading here, the area under the curve, all of that equals to 1. And then everything must be positive. Notice it says greater than or equal to 0 for all possible values. So all of your probabilities, everything will be positive. All right, can I scroll up? All right, continuous random variable is normally distributed. Once again, that's the bell-shaped curve or has normal probability distribution. If its relative frequency histogram has the shape of the normal curve. Anybody holding on to that number 2? All right, so once again, that's the normal curve, that bell-shaped curve. Notice our mean is in the middle, Greek letter mu. Then we have inflection points at your mean plus a standard deviation, then your mean minus a standard deviation. And inflection points are just where the curvature of your graph changes. And so that's what I was talking about right here in this red box, talking about concave up versus concave down. Just basically where it goes from being a U shape to a upside down U shape. That's where inflection points occurs. So they're really not going to focus on the emphasis of inflection points, but pretty much they may ask you in math lab, where are the inflection points? And so that's when you add a standard deviation and subtract the standard deviation from the mean. All right, let's scroll up. That was just what I just mentioned right here. Inflection points, where the curvature of the graph changes. Concave up to concave down. If I scroll up too far, let me know if somebody's still copying. All right, so next we're going to get into properties of the normal density curve. Some of them we already mentioned before. Like the first one, the normal curve is symmetric about the mean. And so that just means that 50% of your data will be to the right, 50% of your data will be to the left, and also it mirrors each other. So that not just 50% will be on the right and left of it, but also what exactly what goes on the right goes on the left as well. So that curvature would be reflected about the mean. Number two, the mean, median, and mode are equal and has a single peak and highest point at the mean. Don't forget the mean is your average. All right, scrolling up. Just mentioned number three already has inflection points. When you add a standard deviation and subtract the standard deviation from the mean. And the area under the curve is equal to 1. So that means if you know one side of a certain data value, and you know the other side, you just subtract it from 1. So if I know that 0.7 is to the left of this data value that I'm looking at, that means 0.3 will be to the right of it because you're doing 1 minus 0.7. All right, so area under the curve is always equal to 1. Right, holding on to number 2. All right, number 5, the area under the curve to the right of the mean equals half or 0.5. And the same goes for the left side of the mean as well. Number 6, as x increases, the graph approaches but never reaches the horizontal axis, which is 0. And the same goes for x decreasing. So that's what this space emphasizes here. That's why I drew that green arrow, just to emphasize whenever you draw the diagram or wherever you see the diagram drawn, there should be a space right here, no matter how far it goes to the right or how far it goes to the left, because it's never supposed to actually reach 0. And number 7 is the empirical rule. Talked about that already. It's just a reiteration of that. But I will scroll up, just trying to make sure everybody's good. Everybody holding on to number 5. So the empirical rule just says that 68% of your data or 68% of the area under the curve is within 1 standard deviation of the mean. 95% of the area under the curve is within 2 standard deviations, and then 99.7 is within 3 standard deviations. Yep, empirical rules still apply. Yep, same empirical rule. Everybody on into number 6. No, if you're talking about right here, that's 1 standard deviation, that's 1 SD. And then here would be 2 SD, and then the next one would be 3 SD. I think that's what you're referring to. Yep, 1 standard deviation. Mhm. All right, can we scroll up? Oh, this part right here is just, well, is everybody done writing before I go to the diagram? I don't know if anybody needs to see this again. It's just diagram just emphasizing the empirical rule once again, and the percentages, the breakdown of the percentages. All right, can we scroll up? All right, so this example here, just reemphasizing the empirical rule, make sure we're okay with it. And this is something that we've done in the past, so it's just reemphasizing that process. There's the birth weights of full-term babies are normally distributed with mean of 3,400 and a standard deviation of 505. I'll just write that. This part is what we would fill out. Of course, that doesn't come with a problem, but just making sure we're emphasizing that. So we'll see how we get those values in a second. But right here is just the problem right here. Giving you a chance to write. All right. So if you remember the empirical rule, the mean is in the middle. That's 3,400 for us. Then we have these data values to the right of our mean, data values to the left of our mean that we have to calculate. So in order to get those values to the right, all you're gonna do is take your mean and add your standard deviation 3 times. So your mean is 3,400. We had 505 3 different times. That gives us 3,905, 4,410, 4,915. So that's how we got the right side of our data values. And then to get the left side, we subtract 505 from each side. Subtract 505 from the mean 3 times. And so that's how we get 2895, 2390, and then 1885. And remember, we also mentioned that these percentages are fixed. Those are not the things that change. These numbers down here change according to the information that you're given, but the percentages stay the same. And that's how you find or that's how you would be able to use the empirical rule. All right, questions on that reminder of how the empirical rule works? And so when you go back to it, we were talking about the birth weights of full-term babies. So that means 34% of your babies will be born in between 3,400 grams and 3,905 grams. And so you can play with percentages in that way. See so much. Well, you got to be more specific when you say how does it work. So you break up the percentages. Like if you want to know what percentage of babies will be born in between these two values, it's 34%. Is that what you're saying? Or 13.5% would be between these two values. Or if you want to know between 3,400 and 4,410, you would add these two percentages together. Oh, those are fixed. So those percentages are always there, 34%. Remember, that goes back to this. These percentages stay the same. So you don't have to calculate those percentages. Yep. You just have to calculate these numbers down bottom, which is what we just finished doing here. And you can't calculate those numbers down bottom unless you have the mean and standard deviation, which is what they would give you. All right. Let's see. Yep, no problem, no problem. Wrong button. All right, so here's just an example of problem that you could see in math lab. I believe they have a problem like this. It's shade the region that represents the proportion of full-term babies who weigh more than. So if you're talking about more than means to the right of when you look at the number line, just generically. Everything that's greater than +1 will be to the right of it. Everything that's less than +1 will be to the left of it. So whenever you say more than or greater than, they assume you know they're talking about to the right. If they say less than, you're talking about to the left. All right, so that's always the case. So in this case, they say more than 4410. So they will give you probably about 4 graphs to choose from. And this would be the graph that you will be looking for. 4410 is shading to the right because it says more than. If it was less than, then you'll be shading to the left of. All right, any questions on what we did there? All right, can we scroll up? Okay, that's it for 7-1. Can we go to 7-2? Anyone still copying? All right, let me see how long is 7-2. I don't think it's that long. Yeah, it's not that bad. Okay, so let's do 7-2. And then we'll go from there. So applications of normal distribution. So we talked about z-scores. We were introduced to z-scores back in chapter 3. And so here we're actually going to look at the application of your z-scores. Excuse me. And so your z-score formula is your data value minus the mean divided by standard deviation. Excuse me. All right. So calculating your z-score will always be your data value minus the mean divided by standard deviation. So you guys will have a chart that we will use, and it's in the appendix on A11 and A12 in the back of the book. Yep. It's a chart that's in the back of the book. Yeah. I'll show you guys what it looked like, of course. See if I already have it pulled up. Now scroll up. All right. So your z-scores will always be rounded to 2 decimal places. So always keep that in mind. All right. So we're going to have a chart that looks like this. And let's say if we're looking for 1.23 on the chart, we're going to break it up. When we look at this 1.23, we break it up into 1.2 and this 3. And so notice how I have this. And 3, the digit that's farthest to the right will be on the top row. And then the 1.2 will be over here on the left. And that's what we'll look for. And I'm going to go to the chart in a second. But just showing you as an idea of what we're doing. If we're looking for 1.23, we break the number up into, like I said, 1.2, which would be down this first column. And then the 03, or just 3, would be up here on this top row. So let me show you how it works. So here's the chart. So you're going to have a negative side, which is, notice how this one starts off with negative 3.4 and it goes down to 0. And then you have a positive side, goes from 0 to positive 3.4. So that's what the 2 pages are. You have your negative and your positive. Now we're looking for positive. We're looking for positive 1.23. So 1.2 is right here, and then the 3 is right here. And then where they meet is the value we're going to pull from the chart, which is 0.8907. All right, so make sure we're clear on what we did. Same thing as if I was looking for, let's say if I was looking for 0.58, where the 0.5 is right here, and then the 8 is right here, and then where they meet is the value that I'm pulling from the chart, which would be 0.7190. So questions on how we pull a value from the chart. Not gonna, we're about to get into what this value means in a second, but questions on how we pull the value from the chart. Okay, so let's go back to our 1.23. So once again, 1.2 is right here, 3 is right here. That meets up right here, 0.8907. So notice at the top of the chart, we have this. And what it's saying is that no matter what value the graph gives you, it always gives you what's to the left of. That's why it shades to the left. So the chart value is always what's to the left of, or the amount of data that's to the left of the value you're looking at, the amount of area that's to the left of the value that you're looking at, or the percentage of data that's to the left of the value. But it's always going to represent to the left of. So if you were to even go to here, once again, notice it's shading to the left. So once again, it always represents what's to the left of. Whatever value you get from your chart will always represent what's to the left of. Now, all z-score charts aren't created equal. So I'm telling you the chart, talking to you about the chart that the book gives you. Now, if you were to get another chart from Google or Siri or whatever, you have to make sure that it's doing or set up in the same way, or you would have to read it or interpret it differently. So what I'm telling you leans on the chart that the book gives you. So so you're going to be safe reading it this way as long as you're using the chart that the book gives you. If you go pulling from somewhere else, another source, there are different types of z-score charts. If you know how to use them, they still give you the same value, but you don't use them the same way or calculate the same way. So once again, I'm just talking about the chart that the book gives you. Okay, so let's go back to the notes. All right, so you see we got the 0.8907. And this purple is what I just mentioned, the chart value will always represent what is to the left of the data value. In other words, less than. You chance to write that. And so don't forget, we all also mentioned that the total area under the curve is going to be equal to 1. So if I know what's less than, I can always figure out what's greater than by subtracting that from 1. Can I scroll up? And so that's what this statement says right here. To find out what is to the right of the value, in other words, greater than, we'll subtract the chart value from 1. All right, scrolling up. Anybody hold on to the green statement? All right, so let's look at this example. And so we're gonna run through a few scenarios, cover all the scenarios using your Z-score chart. There are only 3, and you'll see the 3 scenarios that you will come across. Keywords will let you know and dictate which scenario you would use or be presented with. And we'll talk about those keywords, before we close out. So here we have a pediatrician obtains the heights of her 3-year-old female patients. The heights are approximately normally distributed. That's very key because we did, if they were not normally distributed, then we wouldn't be able to use this process. With the mean 38.72 inches, standard deviation 3.17 inches. So determine the proportion of 3-year-old females that have a height less than 35 inches. I'll give you a chance to write that out. All right. So with all word problems, I like to start writing out my given piece of information first. That's what I did over here in the red. Establish your mean, which is 38.72, standard deviation 3.17. And then the data value, what we're asking a question about or what we're doing our comparison to, we're talking about less than 35. So our data value will be 35. All right. So plug it in Z-score chart. Z-score formula. So that'd be 35 minus 38.72 divided by 3.17. Always round to 2 decimal places. So it's negative 1.17. And now you go to the chart. So I'll go to the chart, just to do the process again. Just give you a chance to write. We're looking at negative 1.17 when we go to our chart. Once you get your z-score, then you go to the chart, get your chart value. All right, so let's go back to the chart. Just make sure we're okay with reading it. So we're looking for, this time we're looking for negative 1.17. So the negative 1.1 is what we're going to go here with, and then the 0.7, what we're looking at right here. So negative 1.1, 0.7, they meet right here at 0.121, excuse me. Questions on that before we go back to the notes? So 0.1210. So once again, chart always gives less than. So that means we would use the chart value because that's what we're looking for, less than. So the proportion of the pediatrician's 3-year-old females who are less than 35 inches tall would be 0.1210. Or if you want to write it as a percentage, 12.1%. You know, it just depends. I believe in MathLab that 0.1210 is okay. But of course, MathLab will let you know what they want from you. All right, questions before we go to the next scenario? Okay, so the next one, notice it says using the previous problem, find the probability that a randomly selected 3-year-old is taller than 37 inches. Yep, if you're talking about plugging into the z-score formula, yes. So if we're using the previous problem, our mean and standard deviation are the same, but now we have a different data value, which is 37. Yes, So remember in the chart, there were negative and positives, z-scores. All right, so when we put that in z-score formula, we end up getting negative 0.54. And so you go to the chart, Negative 0.5 will be on the left column. The 4 would be up top. And that gives us 0.2946 from the chart. All right, so chart always gives less than, but this time we want taller than, or in other words, greater than. So remember I said there will be key phrases that will let you know what you're dealing with, less than versus greater than. If it says shorter, then we'll be looking at less than. But here we talk about taller, then we're looking at greater than. So that means we're going to subtract the chart value from 1. Notice we're doing this with the chart value, not the z-score. The chart value is what we pull from the inside of the chart. So we're not subtracting the z-score from 1, but the chart value. And that'll give us 0.7054. All right, any questions before we look at the next one? All right, third scenario, remember I said there are only 3 different scenarios. So you talk about less than, greater than, and now we're looking at between. Those are the 3 scenarios that you'll be presented. The only 3 scenarios that you'll be presented. So using the previous information, find a probability of randomly selecting a 3-year-old that is between 35 and 40 inches tall. It says inclusive as well. So mean and standard deviation, once again, still the same. But this time we have 2 data values. We have 35 and 40. So I'm just calling 35 data value 1, 40 data value 2. Put both of those in the z-score formula. So 35 minus 38.72 divided by 3.17 gives us negative 1.17. And 40, plug that in, you'll get 0.40. Once you have your z-score for each, go to the chart for each and end up getting 0.1210 here, 0.6554 here. Once again, you go to the chart for each one of them individually, get their individual chart value. Now scroll up. All right, so over here, just giving you a visual as to what's going on. We talk about z-score 1, that 0.1210 represents what's to the left of z-score 1. That 0.6554 represents what's to the left of z-score 2. So if I want to know what's between z-score 1 and z-score 2, I would have to subtract that piece, the purple from the green, and that'll give me what's in the red. So whenever dealing with between, now you don't always have to draw it out, but I'm just giving you a visual like I mentioned. So to find out what's between the data values, you subtract the two chart values from each other. All right, so there we go. 0.6554 minus 0.1210 gives us 0.5344. That's the amount of data or the percentage of data or the area between the two values. All right. Questions on anything up to this point? Let's scroll up. All right. So summarizing your three scenarios, there will be key phrases or keywords that will let you know what scenario you're dealing with. So you're talking about less than, it could just say less than, or if it says something like shorter, colder, below, under, things like that, that will be scenarios for your less than. Greater than, once again, it could just say greater than, but it could say taller, hotter, above, things of that nature that will be considered greater than. And then between, I haven't seen any other word that represents between, but between. But if you're looking at less than, and the chart value that you pull will be the answer. If it's greater than, you're going to subtract the chart value from 1. Then if it's between, you're going to take the two chart values that you pull from the chart and subtract them from each other. So those are your three scenarios that you will be presented. All right, questions? Any questions? All right. So that's 7172. Next class, I'll give you the opportunity to ask questions on anything. So try the stuff out, see if you get stuck. See if you have review the notes, make sure you're good. So I want to make sure you guys are okay before we jump into chapter 8. Once again, chapter 7 is just 2 sections. I do not have to do anything new next class. I will give you guys the floor to ask whatever questions you want to ask about anything. Doesn't necessarily have to be about chapter 7, but about anything before we move on into chapter 8. All right. Questions, concerns, comments before I close out today? Good, very straight. All right. So you guys have a good one. Be safe. Have a great weekend. And I will see you on next class.
Thank you.
Thank you. Have a good one.
Hello?
Yes, sir.
Oh, the first chapter 7 and 8 are the shortest. They're very short, like not many sections.
Right. Uh-huh.
Okay. Okay. And then after that, there's going to be test number 4.
Yes.
Wow. And okay. Oh, I think it's still recording. Okay.
Are you good to go?
Okay. Yeah.
Okay.
To go. I just need I was about to stop by office. I was about to stop by office hours later.
Okay. Now today I had to give a midterm to my calculus class, so I won't be able to do it today. But well, you know what? No, if you know you're gonna come by, let me know. Shoot me an email because I can use another computer.
Okay.
Yeah, if you know you're gonna come by, shoot me an email. I'll just log on with another computer.
Okay. I'll let you. I'll send you an email. I'll let you know.
Okay. All right.
Shoot.
Anybody else before we close out? All right. If everybody's good, you have a good one. And I will see you on next class.
Yes.